All right, y'all are ready for a treat here, I hope, because this is amazing stuff. So you probably have already heard about the sum and the difference identities for cosine and sine. And you probably know that there are these weird formulas, but how do we know that they're true? You might have played around with some numbers and said, okay, well, it seems to work if I pick these particular values, but how do I know that it always works? Well, this is fantastic news, because I can answer that question for you in the following derivation proof for the difference identity for cosine. So remember that the goal here is to find a formula for the cosine of alpha minus beta. Okay? So what we're going to do is, looking at a circle here, unit circle, we're going to graph some generic angle alpha. It's in red. The terminal side of alpha goes all the way down into quadrant 3 arbitrarily. It doesn't have to be in quadrant 3, but that's how it is here. See how the arc goes all the way around through quadrants 1 and 2 and a little bit into quadrant 3. And then we also have another angle, beta. This one is smaller. It doesn't have to be smaller, but it makes it a little easier to think about when the smaller angle is the one that's being subtracted. So that's just going to be a quadrant 1 angle. So if we take this amount of angle, right, and subtract it away from alpha, we're going to work our way back beta away from alpha, we're going to end up at a new place. Okay, so we subtracted alpha minus beta to get to this new place, and it would make sense to call this new angle alpha minus beta. Okay, so the goal is to come up with an equation for cosine of alpha minus beta using the fact that we know about alpha and beta separately, and then we can kind of work our way to the alpha minus beta bit. All right, so the trick to this problem is what we're going to look at is alpha minus beta in two different places. One in standard position. If we go from here all the way around to here, we're going to be looking at the angle alpha minus beta. But also, if we start at beta and we rotate it all the way around to alpha, the distance not the distance, but the angle that we travel is all of alpha except for this chunk right here. So it's all of alpha except for beta. So this is also alpha minus beta. Okay? So that's this angle right, I'll use a different color. That's this angle right here is also alpha minus beta. So it all hinges on the fact that we can look at this angle in two different places, one in standard position and one not in standard position. And what we'll do is we'll connect the endpoints of the angles to create a chord on the circle, right? So since both of these chords subtend angles of equal measure, then those chords are the same length. Going back to a little geometry for you there, right? So again, this arc length rate, or this arc measurement is alpha minus beta from A to C. But this arc measurement here from B to D is also alpha minus beta. So the arcs are going to be the same because the angles of the chords are going to be the same because the measurements of the arcs are also the same. All right, so that means that the length, the distance from A to C is the same thing as the distance from B to D. And that's what, that's the setup of our equation right here, right? We know that these guys are equal. So now we're going to take a look at the distance formula, right? We're going to find the difference in the x values, x2 minus 1. That's my delta x. And the difference in my y values, that's y2 minus 0. That's delta y. We square them and add them and then take the square root. That's the difference formula. And that's going to be the length of AC. Okay, we're going to do the same thing with dB, right? We're going to take difference of the x values of x3 minus x1. That's going to be another delta x value. And then same thing with the y values, y3 minus y1. That's going to be another delta y value. We square them, we add them, we take the square root. That's the distance formula. It's also the Pythagorean theorem. You might recognize that. So now we've got this great equation that's a little scary, but I think we can do some things to this. So let's see some things we can do. Well, first of all, we need to keep in mind what we're looking for. Okay? Cosine of alpha minus beta is, well, the cosine is, and it says y is not the same thing as x2. The cosine of alpha minus beta is equal to x2 because x2 is the x-coordinate of the point on the unit circle that the terminal side of alpha minus beta goes through, right? Remember that The cosine of alpha is the x value, and the sine of where the cosine of the angle is the x value, and the sine of the angle is the y value. All right, so the goal is to try to solve for x2. Right, we're trying to solve for the cosine of alpha minus beta. So x2 only shows up right here, so we're going to try to solve for that. All right, so x2, well, it's inside the square root, so let's square both sides. So we're going to square both sides and get x2 minus 1 squared, it's a 2, plus y2 squared equals, well, we'll square the other side as well. This is actually good all around because it just gets rid of all the square roots. And then it's just a whole bunch of algebra. So we're going to try to solve for x2. Let's see, so maybe we'll go ahead and subtract this y2 squared. So we'll do x2 minus 1 quantity squared equals, I'll go ahead and expand these out as well. So we'll square the x3. We'll do 2 times x3 times x1 minus that because it's the minus sign, x3, x1. And we'll do negative x1 times negative x1 is positive x1 squared. Do the same thing here. We'll do plus y cubed squared minus 2, not y cubed, y3 squared minus 2y3 y1 plus y1 squared. And then don't forget this y2 squared that we're subtracting over here. All right. So remember that these are all coordinates on the unit circle. So x1 squared plus y1 squared equals 1. I mean, the same thing can be said about y2 squared plus x2 squared plus y2 squared is equal to 1. And x3 squared plus y3 squared is equal to 1. In fact, any x value with its corresponding y value is going to work out to be this is the equation of the unit circle. Graph that, you'll get the equation of the unit circle. So if we can find some pairs to pair up here, like for example, x1 squared plus y1 squared, well, that equals 1. Oh, but take a look. x3 squared plus y3 squared is also equal to 1. Oh. Well, that's actually really nice. So that was going to simplify things down. So this green pair is going to be 1, and this blue pair is going to be another 1. And then we have a lot less stuff, right? We've got a minus 2x3, x1, and we've got minus 2x or y3, y1. We still have this pesky y2 squared. But maybe we can do something about that. If we go ahead and just like we did on the right side, maybe we'll expand out the left side. So x2 squared minus 2x2 plus 1. Now this might not seem like a very good idea because remember we're trying to solve for x2, and suddenly we now have x2 twice. But I'm thinking we might be able to eliminate this x2 squared somehow. Okay, so one thing you'll probably notice is that we've got a plus 1 on the left side and a plus 1 on the right side. Those can be subtracted out. Wait a second, hold on. This x2 squared goes nicely with this y2 squared. If I subtract that over, I'm going to get negative 2x2 equals, I still have one of these ones, minus 2x3x1 minus 2y3y1 minus 2 y2 squared, but also minus x2 squared. Oh, goodness. This is exciting. Do you guys see it? This is not the same thing as this equation, but they're both negative, right? So if we multiply the left side by negative 1, we multiply the right side by negative 1. Oh. So take a look. This means that this thing right here is not equal to 1, but it's equal to negative 1, which is fantastic because the negative 1 cancels out with the positive 1. Holy free holies. This is so exciting. So that means that the things I highlighted in yellow are positive 1 and negative 1, and those add to get 0. So we end up with negative 2x2 equals negative 2x3x1 minus 2y3y1. Okay, well, there's a whole bunch of negative 2's that we don't need. Right? We'll just divide it out, right? So we get x2 equals x3, x1 plus y3, y1. That should look like a familiar pattern, but it's not exactly what the cosine difference identity is. But remember that x2 is the same thing as the cosine of the angle that's right here, which is alpha minus beta. So that's why we were solving for x2. But x3, wait a second, x3 is right here. x3 is the x-coordinate of the angle alpha, right? So this is just the cosine of alpha. So this is the cosine of alpha. And x1 would be the cosine of beta for the same reason. And then we've got a plus. And then we've got, oh, wait, these are just the y values of the same stuff. The 3 and the 1, right? The alpha and the beta. So this is going to be the sine of alpha and the sine of beta. This is the difference identity for cosine. Whoa! How slick is that? Nice. So we've proven what the cosine difference identity is with a whole bunch of algebra, but nothing that is foreign concepts, right? These are all just old school concepts. All right, now we could maybe try to do the same sort of thing for the sum, but wait a second. Hold on. We have some other identities, right? Like, for example, if we know that the cosine of alpha minus beta is equal to this, which we know because we just proved it, Q, E, D, then if I wanted to find the cosine of alpha plus beta, I can rewrite it as a difference, right? Adding beta is the same thing as subtracting negative beta. So let's just apply this identity that we now know for sure is true. So we're going to say, okay, this is cosine of alpha times the cosine of negative beta, right? Our second angle is negative beta here. And then the minus turns into a plus, right? So then we do the same thing with our sine. Sine of alpha times the sine of negative beta. But wait a second. We know about odd and even functions. Cosine is you guys tell me? Yeah, you know it. Even function, which means that the negative poof goes away. Cosine of alpha times the cosine of negative beta is the same thing as cosine of alpha times the cosine of beta. On the other hand, odd function over here, right? The sine of negative beta is the same thing as negative sine of beta. So yeah, this is going to turn into, instead of a plus, a minus because the sine is an odd function. And whoa, we've proven, based on this, we've proven that the sum formula is this. All right, so that is a proof of the cosine difference identity and the cosine sum identity. I hope you enjoyed that as much as I did.